for tonight's lecture. Tonight's lecture is given by somebody who needs no introduction, really, because Roger has given us a series of lectures over the last few years, and I have already, I think, persuaded him to come back next year and give us another one. But Rodri is going to talk about something that fascinates me, and I have to say that Nick Hart went to see this place, and it was shut. I think they were doing some work on it, so he wasn't able to do what he wanted to do. But we're going to hear about the great Mount Wilson Observatory. So Rodri,
okay.
Over to you. If you can get rid of that.
Yeah, let me.
Have you got a thing?
It should work.
One of these?
I don't know if it. Yeah.
It's that little one.
Okay, so yes, as Steve said, this is part of my ongoing series of historical lectures. And I've previously spoken about Yerkes Observatory, where I worked for 6 years. Last year I spoke about George Ellery Hale, who set up Yerkes Observatory, and he left Yerkes Observatory to set up Mount Wilson. So my connection with Mount Wilson is more tenuous, although I have been lucky enough to observe there. In 1999 I got I have a sore throat and my voice is really not really good this evening, so apologies for that. In 1999 I got a Mount Wilson Fellowship to make observations of a reflection nebula, the brightest reflection nebula in the sky, NGC 7023 I think, using an adaptive optics system that they've got on the 100-inch, which is the famous 100-inch at Mount Wilson. And the idea was to observe the structure of the dust, or the emission from the dust, I should say, in more detail than had ever been done before, to try and learn more about the way that the dust was scattering light. And we got the time. Myself and 2 colleagues submitted the proposal. We got the time, so I went out to Mount Wilson to use the telescope. No one in the vetting committee had noticed that because of the design of the 100-inch, it couldn't actually point far enough north to look at NGC 7023. And for some reason, they thought it was such a good science proposal, but they failed to notice that the telescope couldn't actually point that far north because of the design of the mountain. But anyway, I got to go there on 4 observing runs, and it is an amazing place. So that's what I'm going to talk about this evening. So this picture shows Mount Wilson Observatory, and we're going to talk about most of the things you can see. This, of course, is the 100-inch, the 60-inch telescopes. So those are the 2 telescopes. These are solar towers, the 150-foot and the 60-foot, and here is the snow telescope. So I'm going to talk about those 5 facilities, I should call them, and a little bit about the history of the observatory. I'm assuming I can't move this with the remote. Maybe I can, I don't know. Okay. So this is a summary of my talk. I'm going to first of all talk about when Mount Wilson Solar Observatory was set up, and it didn't drop the name solar until 1908. So it was Mount Wilson Solar Observatory when it was set up, and then dropped the solar in 1908. I'll talk about the snow telescope, which was the first telescope to be used there, the 60-foot solar tower, the 60-inch reflecting telescope, the 150-foot solar tower, and the 100-inch reflecting telescope. So this is kind of in chronological order of when these facilities became available, and I'll briefly discuss what's happening at Mount Wilson today. Give me 2 seconds. Okay, so here's a sign, and you can see that it was founded by George Ellery Hale, the person who set up Yerkes Observatory, in 1904. So he left Yerkes in 1903. He tried to persuade the University of Chicago to make Mount Wilson a new observatory part of the University of Chicago. They refused, so he quit University of Chicago. He quit his professorship and struck out on his own, not part of any university, to set up Mount Wilson. As you can see, now it is operated by the Mount Wilson Institute. So it was the money for the setting up of the observatory came from the Carnegie Trust, which had just been established in 1902. Andrew Carnegie bequeathed huge sums of money to all kinds of things, including scientific research, and Hale jumped on that opportunity, got funding from the Carnegie Foundation to start Mount Wilson Observatory, and then it was handed over to Caltech in the 19 1920s, I'm guessing, when Caltech was established. Now it is no longer part of Caltech, the California Institute Zone. It's run by a private institution, the Mount Wilson Institute. And this is where it is. Okay, so here is the Los Angeles Basin, Long Beach. Los Angeles doesn't really have a center. If you've ever been there, it's the most dreadful place on earth. Pasadena is there, which is where Caltech is based, and in the mountains kind of behind Pasadena is Mount Wilson. Now, it benefits from exceptional seeing. The 4 occasions I've been there, every night, if it was clear, and it was clear most of those nights, the stars do not twinkle. They are steady as anything. It has the best seeing of anywhere in the continental United States. And that's because of the inversion layer that is formed over the Los Angeles Basin. It's the same inversion layer that traps the smog and causes Los Angeles to be such a dreadful place to live in. But it leads to exceptional seeing at Mount Wilson Observatory. And that has implications for the way that Mount Wilson is used today. Because obviously with however many gazillions of people living in this area, the light pollution is dreadful. But the light pollution hasn't affected the seeing. It just affects how well you can see faint objects. Okay, I'm actually not going to center this. When I started preparing this talk, I thought I would talk more about these 3 characters. I'm not really going to, but anyway, let me just mention them. So Hale set up the observatory. Walter Adams, who had been at Yerkes with Hale, came to Mount Wilson, and by the early 1920s, Hale was suffering increasingly from mental problems. It's now generally recognized he was schizophrenic, and so he would disappear for long periods and go into essentially mental hospitals, or sanitary or whatever. And so Adams ran the observatory and then eventually took over as the director when Hale stepped down. And then, of course, Hubble needs no introduction. He is probably the most famous astronomer to have worked at Mount Wilson Observatory. So let me talk first of all about the establishment of the observatory. So Hale left Yerkes in 1903. As I say, he struck out on his own. He tried to persuade the University of Chicago to set up Mount Wilson as a remote observing station. They said no, so he just quit his job. And he established Mount Wilson with money from the Carnegie Foundation in 1904. So it wasn't part of any university. It only became part of Caltech in the 1920s, and then Caltech passed it on to the Mount Wilson Foundation, I think, in about 1980s. So the initial funding came from the Carnegie Foundation. And the first telescope to be installed at Mount Wilson in 1904 was the SNO solar telescope. Now, those of you who heard me talk 2 years ago about Yerkes Observatory will remember that the SNO telescope was at Yerkes. Let me remind you. Well, first of all, this is a couple of pictures of Hale looking very much the adventurer in 1904. So, looking at what is about to become the observatory. And here are some pictures of taking the equipment up to the peak. The peak is at about 7,000 feet, and there was no road initially, so they had to blast basically a ledge, maybe about 3 meters wide, and everything was carted up by horse and cart and donkey and cart, and then a little bit later vehicles. But bear in mind that the first telescope up there, the SNO, was 1904. There weren't any vehicles that could make it up in 1904, so it was all done by horse and cart. Now you can, of course, just drive up, but so this is Yerkes Observatory. That's the south tower of Yerkes Observatory, and this is the SNO telescope. So this was a solar telescope that Hale built whilst at Yerkes. It had a 24-inch mirror, and basically this long thing here was to try and keep the air cool for observing the sun. So that was built at Yerkes in the sort of 1902 period. I can't remember exactly when. But no sooner had it been built, just a few weeks later, and it caught fire. And the whole structure burnt, but luckily the mirror wasn't damaged. So when Hale went to Mount Wilson, he took the mirror with him, this 24-inch mirror, and basically built a new solar telescope at Mount Wilson, which was called the SNO, because it was a lady, Mrs. something or other Snow, given the money to Yerkes, to Hale, for the the telescope you saw in the previous picture. So this was the building of the snow solar telescope at Mount Wilson. 24-inch mirror, and it was really, it proved how good a observing site Mount Wilson was for daytime observing. Now remember, Hale was primarily interested in the sun. He never did any research on anything except the sun. So he wasn't really too fussed what an observing site was like at night time, but daytime was all important to him, and Mount Wilson showed that the observing conditions were very, very good for doing solar work. And just to briefly show you how a solar telescope works, of course, the problem with a solar telescope is you've got so much heat coming from the mirrors that you've got to build a slightly different design to try and keep things cool. So here you have the primary mirror, and basically here you've got the sun, bounces off a flat mirror, which is called a coelostat, which tracks the sun, bounces off another flat mirror onto the primary mirror and then onto the focal plane. And the longer you can make these distances, the more you keep the heat down, which is why, as you can see, Hale built a 60-foot tower, then a 150-foot tower. The longer you can make these distances, the more you can keep the heat down. So, 1904, Hale started using, Mount Wilson astronomers started using the snow telescope, and by 1908, it's only 4 years later, Hale was building the 60-foot solar tower, and here are some pictures of it during construction. So as the name implies, basically rather than having a horizontal structure like you had with the snow telescope, you've got the coelostat at the top here, and then you do the observing way down at the bottom. And this improves on the thermals rather than having it at ground level, so it improves on the steadiness of the image. So this was built in 1908, and there's a nice picture of it showing this is the snow telescope next to it. So it's right next to the snow telescope, 60-foot high tower. And almost immediately, Hale made a major discovery. So the telescope had barely been completed when, in 1908, he made his most famous discovery, and that was that he showed that sunspots were regions of intense magnetic field. And the way he did that was to notice something called Zeeman splitting. So when you look at the spectral lines produced by atoms and molecules, when those atoms and molecules are placed in the magnetic field, the lines split. And that's called Zeeman splitting. And it's due to a quantum mechanical effect that wasn't understood until the 1920s, really. But the effect was known since the 1880s, 1890s, and named after Zeeman. So Hale noticed that whereas there was no Zeeman splitting on the general surface of the sun, as soon as he looked at the spectral lines where there were sunspots, he saw Zeeman splitting, showing that they had an intense magnetic field. So that was Hale's major scientific discovery of his career. And this is the paper announcing it. I'm not sure which journal, but on the probable existence of a magnetic field in sunspots. So you can find that online. I just did a Google search for it and it pops up. All of these old papers have been scanned, so you can look at them for free. So that was the announcement in 1908. And in the same year, so he was a busy man, they built and completed the 60-inch reflecting telescope for, obviously, for nighttime observing. Now the glass disc had been made back in 1894 by the Saint-Gobain company in France, and Hale's father had bought it way before Yerkes ever existed, and well, when Yerkes was in preparation. And Hale's father had given this 60-inch glass blank to Yerkes Observatory as part of the deal he did with the University of Chicago to employ his son. So this glass blank had been lying around for over 10 years, and when Hale started conceiving of building a 60-inch reflecting telescope, he pulled out this 60-inch glass blank from his drawer and got George Ritchie and others to work on figuring the shape into a parabola. And there's an excellent website, part of the Mount Wilson website, where you can read about the development of each of these facilities, and it goes into quite a bit of detail about the 60 inch. It seems to me, having read through this website in the last couple of weeks, it goes into more detail about the 60 inch than it does about any other of the others for some reason. And they had all kinds of problems with the mirror. It was all ground, of course, by hand back in those days, and you need to make it into a parabola to avoid spherical aberration. But they didn't quite get it to the right figure, so then they had to redo it, and it led to delays, but it did go into operation in 1908. So this is the building of the telescope structure, or rather the dome and everything. And this is the telescope itself, and it's a beautiful telescope. And I've been lucky enough to look through this. It is now primarily used for public observing. So I think it is every week, one evening a week, you can go up to Mount Wilson and look through, if it's clear of course, look through the 60 inch. And when I was there, on the 4 occasions I was there, I looked through it several times, and I remember looking at Saturn through it for example. So it's a beautiful telescope and basically accessible to the public. Just to talk a bit about some of the research that was done with the 60 inch, it has made quite a large contribution to astronomy. It's kind of overshadowed by the 100 inch and the amazing achievements the 100 inch made, but the 60 inch has played an important part. First of all, it played a vital part in developing what's called the Morgan-Keenan spectral classification of stars. Now, if you take a step back, I'm sure you all know of the so-called Harvard system of classifying stars, which is OBAFGKM. Yeah? That was developed in the 1880s, 1890s by Harvard University. But then in the 1920s, 1930s, William Morgan, working at Yerkes, and his colleague Keenan, developed a more sophisticated system, which was still based on the OBAFGKM, but they were able to differentiate between whether, for example, a M-type star was a dwarf M-type on the main sequence, or whether it was a red giant. And you can determine that through looking at the spectral lines in detail, because the surface gravity is different for the two types of stars, and so the pressure broadening is different, and there are subtle differences that you cannot see unless you get a really good spectrum, and the 60 inch was able to provide those kind of spectra. So the Morgan-Keenan spectral classification system was basically developed using spectra taken with the 60 inch. I should mention that when Hale went to Mount Wilson from Yerkes, there was a very strong connection, obviously, with Yerkes, the observatory that he'd set up. So people who stayed working at Yerkes would go out to Mount Wilson regularly to observe, and Hale would try and poach the best people from Yerkes to come and permanently work at Mount Wilson. But there was always a back and forth. So Morgan never left Yerkes. He went there as a 23-year-old graduate of English, can you believe? Hadn't done a degree in astronomy, done a degree in English. He never left Yerkes Observatory, but he would go out to Mount Wilson to observe on a regular basis. It also was powerful enough to take spectra of these so-called spiral nebulae. Now, spiral nebulae, people have been studying them for decades, or for centuries really, but in the 1880s, 1890s, 1900s, people were trying to take spectra of them, but the telescopes were not powerful enough to get a decent spectrum of a spiral nebula. The 60 inch was powerful enough, and what astronomers found using the 60 inch was that the spectrum of, let's say, Messier 31 or Messier 33 was different from the spectrum of the Orion Nebula M42. They are fundamentally different, and that is, of course, because we now know M42 is what we call an emission nebula, and M31 and M33 are distant galaxies. It was the first telescope to have an adaptive optics system fitted in the 1990s, and that is because of the very steady air above Mount Wilson. It's a perfect place to test adaptive optics system. So, as I say, although the 60 inch has been very much overshadowed by the accomplishments of the 100 inch, it has made its contribution to 20th century astronomy. The next on the list of facilities, and notice A year later, they started construction of the 150-foot tower. So the 60-foot tower was completed in 1908, and 1 year later they start on something that's essentially 3 times the height. So you can just imagine how incredibly busy Hale was in getting funds for all of this stuff. So it was completed in 1910, only 2 years after the 60-foot tower had been completed. And in 1911, Adams, who, as I mentioned, took over as director when Hale's mental health deteriorated, he started a program to study the differential rotation of the sun. As you probably all know, the sun takes about 30 days to rotate, but the equator and the poles rotate at different rates. And that is something that Adams studied in 1911 and onwards using the 150-foot tower. 1914, Hale studies the polarization of sunspots. And he discovered that the polarity is opposite in the northern and southern hemispheres of the sun. So in other words, sunspots always come in pairs. One is the north pole of the magnet, the other one is the south pole. But let's suppose the north pole is leading the south pole in the northern hemisphere, in the southern hemisphere it's the other way around. And they swap every time there's a solar cycle, every 11 years it swaps around. We don't really understand the reason why, as of yet, but Hale was the first person to discover that. Also detailed studies of solar prominences. I don't need to explain to you what those are. It is today run by the University of California, Los Angeles. So they run this 150-foot tower, and when I was there, I went up the tower. It's a fantastic experience. You go up in a tiny little caddy that can only take 2 people. You don't, well, there's no health and safety precaution. You fall out, you fall out. I mean, the barrier is kind of below your waist, so you've got to, you've got to not be too worried about heights to go up it. And there's the website if you want to find out more about the 150-foot tower. So now it is entirely run by UCLA, and they still use it every day to do their solar research. It's their main, I think it's their main solar research facility, or at least main solar research facility here on Earth. They obviously use satellites like SOHO and whatever, but it's their main Earth-based solar observatory, UCLA. They essentially have exclusive use of it. And that's a nice picture of the 150-foot tower. Essentially the same design as the 60-foot, just longer to keep the thermals even lower, suppress the thermals even more. And let's finally move on to the 100-inch, which of course is what Mount Wilson is most famous for. So the 100-inch is also known as the Hooker telescope because John D. Hooker put up the money. So this was the first facility. The Snow telescope had essentially been paid for by Mrs. Snow, I don't know his name, and then some money from Carnegie. The 60-foot solar tower, the 60-inch reflector, and the 150-foot solar tower, all paid for by the Carnegie Foundation. The 100-inch was the first facility at Mount Wilson to be paid for from another source, and it was John D. Hooker, who was a prominent business person in the Los Angeles area. I don't remember how he made his money, but he had a lot of it. And it was the largest telescope in the world from its completion in 1917 right through until the completion of the 200-inch Mount Palomar telescope in 1948. So for just over 30 years it was the largest telescope in the world, and there's a nice picture of it. And this is the telescope that I got to use when I was there. It's a beautiful telescope, absolutely gorgeous. The dome is massive. And the mirror is just made of normal bottle glass, and this always caused a problem. In fact, when it saw first light in 1917, when they first looked through it, they thought that a dreadful mistake had been made because the star that they were looking at looked horrible. And what they learned over the next few weeks is that the mirror just takes a long time to cool down from the daytime temperature to produce its correct shape. So unlike modern mirrors, which are made of very, very low expansion glass, this is in the days way before such glass existed, 1917. So when I used it, you basically can't use it until about 3 hours after sunset because it's cooling down.
Can I ask, please?
Yeah, of course.
Why haven't they considered replaced it then with the current?
It would be fun. the money is just not worth it. I did take pictures when I was there in 1999-2000, but unfortunately they are pre-digital, and I've got so many thousands of pictures scanned taken over the last 30 years. I don't know where my pictures of Mount Wilson are. They are somewhere, and one day I'll find them. But I do have pictures of using a telescope and pictures of the glass. And you can see it just looks like bottle green glass, just like that China glass you have when you buy a glass bottle. It looks green. You can't really see in this picture, but it does have a yoke mount, which, as I say, basically stops it from pointing north of about 70 degrees declination. So NGC 7023, which is a 70-something, close to 80 degrees declination, was never going to be observable from this telescope, but no one spotted it when they gave us the time. So you had to look at a couple of other reflection techniques instead.
When did you find that out? First night?
No. When we were planning the observing, I got in touch with the guy who was going to be supporting me, and he knew that it wouldn't point that far north. No one on the selection committee knew, because I don't think any of them had ever used a telescope. They were just experts in the science that we were proposing. The observing assistant was the one who said, "Well, you're not going to be able to look at this object; it's too far north." Okay, so some of the major discoveries. 1923, Hubble showed, using the 100-inch, that Messier 31, the Andromeda Galaxy, was outside of our Milky Way. Now, I do have a separate talk on that, but basically he observed Cepheid variables in Messier 31, and from the already known distance luminosity relationship for Cepheid variables, he was able to show that there's no way it could be inside the Milky Way. 1929, probably the most famous discovery at Mount Wilson, Hubble and his observing assistant Woodson find that the universe is expanding. And in the 1930s, Fritz Zwicky used the 100-inch to find evidence for dark matter in clusters of galaxies, work that was overlooked for about 50 years, until Vera Rubin came along in the 70s and found evidence for dark matter in spiral galaxies. It's possibly because Fritz Zwicky was a very prickly character, generally disliked by almost everyone. And in the 1940s, Walter Bader, who was German in origin and was allowed to work during the war, because being German he wasn't allowed to do any sort of classified war effort work. So he actually benefited twofold from the war going on. First of all, no one else was competing with him for the telescope because they were all off doing war work, science work in the war effort. He wasn't allowed, being German. And secondly, because Los Angeles had a blackout, it was as dark in the 1940s as it had been back in the 1910s. So two things enabled him to do a very important bit of work using the 100-inch, and that was to find that stars are either population 1 or population 2. That's to do with their metallicity, how many elements heavier than helium they have. Prior to this discovery, everyone thought stars were essentially the same chemical composition, and he was able to show that they fell into roughly two categories. Population 1 have less heavy elements, and population 2 have more heavy elements. And population 0 have never been discovered, but they would be stars that only have hydrogen and helium. We've never discovered population 0 stars yet, but presumably they exist somewhere in the early universe. So, for example, the stars in the disk of our Milky Way are mainly population 2. They have a lot of heavier elements in them. Our sun is a population 2. Whereas the stars towards the bulge of our galaxy are mainly population 1. They have fewer heavier elements, suggesting they haven't been through so many cycles of death and rebirth. So those are just some of the highlights that the 100-inch. Oh, and talking of Zwicky and Bader, Fritz Zwicky was such a prickly character that Bader refused to work on the mountaintop with Zwicky unless there was someone else around to make sure that Zwicky didn't attack him. So this is the paper announcing that Messier 31 is in fact outside of our Milky Way galaxy, and the key thing I've highlighted here is the period luminosity relation from the Cepheid variables was found. So Hubble was the first person using the 100-inch to spot some Cepheid variables in M31. And it says here, comparisons of period luminosity diagrams indicate that M31 is about 0.1 of a magnitude or 5% more distant than M33, which as you probably know is a companion galaxy of M31, and about 8.5 times more distant than the Small Magellanic Cloud. Using Shapley's value for the cloud, we find the distance of M31 to be 275,000 parsecs, which is roughly speaking 1 million light years. Now that was revised up to 2 million when they realized there were two types of Cepheid variables, population 1 type and population 2 type. So, but even with this underestimate, this is about half of what we now think M31 to be. This was way too far away to be inside the Milky Way galaxy. So it was the smoking gun that showed that M31 had to be outside our Milky Way. And then now notice, Hubble never ever ever said that he had discovered the expansion of the universe. He basically said that he had found a relationship between how quickly galaxies are moving away and how far away they are from us. The most natural interpretation is that the universe is expanding, but Hubble himself never said that. Now I was reminded today, because I looked it up, I could only remember it a little bit, but a colleague of mine said, when I said, oh, Hubble discovered the expansion of the universe, he said, oh, Hubble and Humason, but Hubble would always take credit for something, even if other people had been involved. And it reminded me of Bill Bryson's description of Hubble in his book, Short History of Nearly Everything. When he introduces Hubble in his narrative, he says that huge, massive ego that was Edwin Hubble. So, by all accounts, Hubble was very, very full of his own self-importance. He'd gone to Oxford in 1914 as a Rhodes Scholar, and for the rest of his life had a fake British accent, even though he'd grown up in Missouri and had moved to Chicago area, a place called Evanston. After a year in Oxford, he developed a posh Oxford accent. His pipe was all part of the image, and he very much was full of his own self-importance. But interestingly, he never said he discovered the expansion of the universe. He just said he discovered this relationship. And this is the original plot. There aren't many galaxies here, actually, but we now know that this is true for thousands of galaxies. So on the x-axis, you have how far away the galaxy is in parsecs, and on the y-axis is how quickly it's moving away. And you can see that obviously there's a bit of scatter, but there's a very good relationship. And as I say, the most natural interpretation of this is that the whole universe is expanding, so something twice as far away is moving away twice as quickly if you have uniform expansion. And a couple of pictures of the 100-inch. Now, Einstein visited Mount Wilson in 1931, so there he is looking through a telescope. Now, as you all know, Einstein was a theoretician. I'm sure he didn't even know which end of a telescope to look through. So this is very much a staged picture. There's Hubble, hovering with his pipe, and this is Adams. And there's another picture then in front of the 100-inch. So Einstein went to the United States in, I think it was 1921, when he had become world famous for general relativity. He became a celebrity when Eddington showed that starlight was bent by the sun. And in 1921, I think it was 1921, he went to the US and apparently said there were two places he wanted to visit, Niagara Falls and Yerkes Observatory. And there's a wonderful picture of him standing in front of the 40-inch at Yerkes. He went back several times to the US, and in 1931, I think this was his first visit to Mount Wilson Observatory, and obviously wanted to look through the telescope that had shown the universe was expanding. 2 years later, of course, he defected to the US. Okay, so to summarize, Mount Wilson Observatory was the most important observatory in the world from 1908 to about 1948, and was superseded then by the Mount Palomar 200-inch. It wouldn't have existed if it hadn't been for the tireless efforts of George Ellery Hale and his incredible ability to raise funds. And, not that this is a talk about Hale, he was responsible for the 4 largest telescopes in the world from 1897 through to the 1990s. The Yerkes 40-inch, then following on from that the 60-inch, following on from that the 100-inch, and then the 200-inch. So basically, for the best part of a century, the largest telescope in the world was due to Hale. Now, it's still an important observatory. Obviously, its ability to do deep sky work is completely nullified by the light pollution of Los Angeles, but because of the incredibly steady air, which means that it is usually sub-arc second. As I say, the 4 occasions I've been there, and most of the nights I was there on those 4 occasions, it was clear. The stars do not twinkle. Even way down towards the horizon, they just rock steady, which I've never seen at an observatory. Any other observatory, including Hawaii, I've never seen that steadiness of air, even Mauna Kea. So it's used as a testing ground for adaptive optics, and in the 1990s, it started being used in the 1990s for the very first testing ground for adaptive optics. Adaptive optics, if you don't know, is a system where you have a deformable mirror that changes its shape very rapidly to try and keep the star steady. So it's trying to compensate for the seeing, and it works. It's a system that works. It was first tried out at Mount Wilson because of the very good seeing, because obviously it's easier to correct when the seeing's already good than if you go to a really bad place. When I was there in 1999, 2000, I was using an adaptive optics system on the 100-inch, and today it is the testing ground for the next thing that we're going to try and do in optical astronomy, which is optical interferometry. Now, as you probably know, we've been doing radio interferometry for decades, linking up radio telescopes that are very distant. But of course, radio waves are millions, billions of times longer than visible light waves. And therefore, to do interferometry with visible light, you have to have precision, which is 1 billion times better. And that's extremely difficult. But there are experiments going on at Mount Wilson today where they have several telescopes set up around the observatory trying to create an optical interferometry and taking advantage of the very steady air that Mount Wilson enjoys. So I will finish there and be happy to answer any questions that you may have.
Thank you, sir. Any questions for our speaker, please?
Before my voice goes inside. Yes.
Well, just a comment about Hubble.
Yes.
And his ego. I've also read that he claimed to be something of a pugilist, and that if you look into it, or when it's been looked into deeper, he wasn't into the boxer, but not with the prowess.
He very much exaggerated his sporting prowess. Yes, absolutely. Yeah, I was reading that in the last few weeks, that his claims of being a boxer of some repute were grossly exaggerated. So he did his PhD at Yerkes Observatory, and the telescope he used for his PhD thesis, where he studied spiral nebulae, he took photographs of them, no spectra, photographs, was a 24-inch telescope, which is no longer at the observatory, it's at the Smithsonian. But that telescope was located directly above where my office was. So he got his PhD from Yerkes in 1917 and went straight out to Mount Wilson to use the 100-inch. And Hale was able to poach him from Yerkes by saying, well, look, we've got this brand new telescope, it's bigger than any other telescope in the world.
The other thing I have read about Hubble is that when he was a student at some American university, I don't know
University of Chicago he went to.
He heard a lecture by an American astronomer called Vesto Slipher.
Right, yeah.
And this was presented at the American Astronomical Association, and after Vesto Slipher had given this talk on the expanding universe and the spectra which he got of different galaxies, only a few mind, the whole audience sprang to its feet and cheered him for a long time because it was so novel, this idea that the universe could be expanding and galaxies shifted their spectra according to their speed.
Yeah.
And Hubble was there in the audience, so I think this is perhaps why he was sort of aware of this later on, and he never really claimed to be the, I mean, he almost did, but he sort of just stopped short a little bit because he had heard the original idea maybe 20 odd years before.
Yeah, in the 1910s at Flagstaff Observatory, Lowell Observatory in Flagstaff, Lowell Observatory. Slipher did work where he showed that nearly all galaxies were moving away from us, with Andromeda being the exception. He never joined the dots, he never found a relationship between how quickly they were moving away and a distance, which of course is what Hubble did. So Slipher himself wasn't able to say that this was an indication of an expanding universe, but he said, isn't it strange that all these galaxies are moving away from us? So he kind of missed his chance, and as you say, probably took that chance.
He must have had much inferior equipment, I guess.
Yeah, he would have been using, I'm trying to think which telescope he would have been using at Lowell Observatory. It wouldn't have been anything like as big a telescope, and they thought the spectrum wouldn't have been anything like as good as Mount Wilson. And Flagstaff is not a brilliant observing site, I mean, it's pretty good, but it's nothing like as good as Mount Wilson.
What limitations on the actual spectrum of the light signals received is there? Can you see beyond the ultraviolet at all, or beyond the...
It entirely depends on your detector. So there are spectral lines in the infrared and the ultraviolet. They don't get to the ground because of the effects of the atmosphere. But, for example, there was a satellite which could still be in operation called the IUE, the International Ultraviolet Explorer, which was the first satellite to take ultraviolet spectra of stars.
about the lenses?
No, basically you can use the same lenses or mirrors for ultraviolet, optical and infrared. It's the detector that you would need to have different, and with ultraviolet and most of the infrared doesn't get to the ground, so you don't go into space to do it. But you can learn a lot about stars by looking at the spectra of the
You get
infrared.
the factor index correction to it.
With a mirror, it doesn't matter.
No, the mirror, but you've actually got to go through a lens.
Yeah, no, you don't. No, you avoid going through a lens.
No lens?
Yeah, you avoid going through a lens. You don't want to use lenses if you can avoid it because they produce chromatic aberration. Talking of lenses and things, one of the interesting things about the 200-inch telescope that Hale was responsible for is by then the so-called Ritchie-Chrétien focus, optical, what's the right word I'm looking for? The Ritchie-Chrétien optical configuration has become standard in telescopes where you have a parabolic primary and a hyperbolic secondary, and it removes coma, right? And the 200-inch Mount Palomar does not have the Ritchie-Chrétien optical configuration for one simple reason, and that was that in the 1920s, Hale and George Ritchie fell out big time. Hale felt that Ritchie was going around claiming praise for work that he hadn't been wholly responsible for, and Ritchie was someone who'd been working for Hale for decades, employed by his father back in the 1880s, 1890s. So they fell out big time, and Hale basically ensured that Ritchie would never get a job. He sacked him from Mount Wilson and ensured that he wouldn't get a job at any other US observatory, which is why Ritchie ended up in France. And because of the bad feeling between them, he refused to have the Ritchie-Chrétien optical configuration on the 200-inch, which basically means it's not as good as it could have been. But Hale, for all his brilliance, was also like a lot of highly driven people, was very vindictive when someone crossed him, and he never forgave Ritchie for claiming work that wasn't really his back in the 1920s, and basically ruined Ritchie's career.
Could I ask you how the adaptive optic system works on a single mirror? Because it's obviously an old mirror, you said, isn't it?
Yeah, no, you've got primary mirror, but then between the primary mirror and where you're collecting the light to your camera or whatever it is, you have this deformable mirror. So it deforms hundreds of times a second using little actuators, which are all computer driven. So basically there's a feedback where it tries to keep the star as sharp as possible, and is continuously feeding back to keep it as sharp. So they're very, very successful. They work incredibly well. If you go on the web and look for examples of adaptive optics, you can see a star that looks like a blob, and then you turn the adaptive optic system on and suddenly it becomes sharp. And they're incredibly successful. A lot of people have said that if it weren't for the need to go into space to see wavelengths that you can't see from the ground, that nowadays adaptive optics has become sufficiently good that you don't need to go into space for the improved resolution, which is of course one of the reasons for Hubble was to get better resolution. We can now get that resolution from the ground with adaptive optics. So the Keck telescopes have adaptive optics. Most major telescopes now do.
Anyone?
I want to mention one other person that you talked about, and that was Milton Humerson.
Yeah.
His story is amazing.
It is.
Isn't it?
Yeah.
Because,
Yeah.
I mean, he wasn't an English graduate that goes and does
I don't.
astronomy.
He never even finished college.
Yeah.
He was working as a bellhop or something, or bellboy, whatever the right term is, in a hotel on Mount Wilson. When he heard that they were establishing an observatory, he wanted to get involved, so he was basically helping drive the mules up there. And then just, yeah, he was. And then he wasn't educated at all. And then he just hung around, and eventually they gave him a job helping couple with his observations. And I mean, in terms of who made the observations, he must have probably made most of them, because of course, being a lackey, he was going to do the tough work.
Spade work.
Yeah, he was going to do the spade work, because Hubble had to smoke his pipe and looking forward. Couldn't do all the hard work.
He must have had a very patient wife as well, because they were going to set up a fruit farm.
Yes.
And he decides that he wants to be a janitor at the observatory to begin with. It was while he was in that role, he was learning the ropes.
Yes, there's the whole countryside around Mount Wilson, they grew a lot of fruit before it all became paved over with people, a lot of orange trees and wineries and things.
Talking of lackeys, so when you make your trips to these observatories, do you yourself do the imaging, or do you get the...
I don't have a lackey, so I do it, yeah. Well, whenever you go to an observatory, there's someone on site who is your observing assistant, and they know how to operate the telescope. So, unless you've been to an observatory several times, each observatory uses a different system. So you can't just walk into an observatory and know how to move the telescope or, change the exposure on the camera. The observing assistant will do that for you, but you're basically saying, well, this is what I want to observe next, and what have you.
So you are a hands-on
Yeah.
astronomer.
Yeah. And it's funny, when I was a PhD student, you could take as long as you like on an observing trip. So when I was in the second year of my PhD, I got a couple of nights observing time on the UK infrared telescope in Hawaii, on Mauna Kea, and a month before, 2 nights on the Anglo-Australian telescope in Australia. So I spun that out into a 2-month trip. Whereas, of course, now all you do is you fly out, make your observations, and fly back. You haven't got the time to. So more and more observing is becoming remote, where you can do it over the internet. And the telescope that I mainly use now through my connection with Chicago is the 3.5-meter telescope in New Mexico called the Apache Point Observatory. And I've only ever been there once, even though I've used it dozens of times, because you basically operate it over the internet with a GUI interface. And there is an observing assistant there, mainly to keep an eye on the weather and things like that. But otherwise, you entirely operate it over the internet with a brilliant GUI where you say, okay, this is the object I'm going to go to next, click a button and it goes. And he or she is just there just to make sure everything doesn't break down. And more observatories are becoming like that. So, for example, a lot of UK astronomers can observe using Hawaii telescopes in the daytime because of the time difference. You don't have to leave your office. The bad side of that is you don't really get into observing mode. You still carry on doing your day job, and then you're observing at night. Whereas when you do go on an observing trip, you think, okay, I'm going on an observing trip, I've got to make sure I know what I'm going to be doing. It's a whole event. Whereas when you're just doing it as part of your everyday job, you don't really, I personally find I don't pay as much attention to it because it's just something tacked on at the end of the day rather than a proper trip.
Okay. Well, thank you, sir.
You're welcome.
Can we show our appreciation, please? Would you be so gracious as to take my ticket out?
And I am more once again. Just one, is it?
Just one, sir. And what do we have? Are you ready for this? Wow. No, it's not mine. 4, 5, 3. Mavis